When trading raw bulk materials like coal or iron ore, the financial stakes scale rapidly. A single maritime shipment involves tens of thousands of tons of cargo. Rough volumetric estimates are commercially useless at this scale. Because these commodities are purchased on strict fixed price per ton contracts, buyers demand the absolute precise mass of the materials sitting in the hold. You cannot batch weigh that much loose material with perfect accuracy as it loads, and it is physically impossible to construct a mechanical weighbridge capable of supporting a 500,000-ton vessel without it instantly shattering. The logistical solution is to calculate the mass of the completely empty ship and then mathematically subtract that value from the total mass of the fully loaded ship. This forces operators to look past the concept of a mechanical scale and treat the ocean itself as a massive, fluid instrument of measurement. The physical laws required to execute this measurement were documented over 2 millennia ago by the Greek mathematician Archimedes. The principle of flotation dictates that a floating vessel displaces a volume of fluid that is perfectly equal to its own mass. Because of this equilibrium, determining the ship's weight is entirely a matter of geometry. We simply need to measure the exact volume of water the hull has pushed out of the way. Calculating the displaced volume of a highly asymmetric 300-meter steel hull cannot be done with manual measurements on the day of departure. Naval architects pre-solve this problem. During the design phase, they meticulously map the three-dimensional geometry of the hull to produce a hydrostatic loading table. This mathematical model correlates exactly how deep the ship sits in the water to the precise volume of fluid the hull is currently displacing. The function runs precisely in reverse. Mapping a known physical draft depth instantly reveals the total displaced volume. Because the geometric labor is already complete, the physical depth of the hull, its draft, is the single real-time variable the crew needs to extract. That depth is read from a vertical stack of numbers welded and painted directly onto the steel, known as draft marks. The baseline for this scale sits at absolute zero along the flat bottom of the ship's keel, counting continuously upwards. This diagram outlines the globally standard metric reading. The numbers represent essimeters, but they skip odd units to count upwards in increments of 2, 20, 22, 24. By international standard, the painted digits themselves are strictly regulated to be exactly 10 centimeters tall. If the waterline rests perfectly flush with the flat bottom of the 22, the draft is exactly 2 meters and 20 centimeters. If the water rises and covers the number to touch the top edge, you add that 10-centimeter height. The draft is now 2 meters and 30 centimeters. By observing precisely where the water level slices across these physical 10-centimeter blocks, a deck officer can interpolate the depth down to a single centimeter. Standardizing these physical dimensions turns a coarse visual scale into a high-precision surveying tool. Reading a single draft mark only yields a mathematically true volume if the ship is sitting perfectly upright and perfectly level. Real-world operations inevitably cause the vessel to list side to side or trim deeper at one end than the other.
Officers conduct a 6-point draft survey, reading marks at the bow, amidships, and stern on both port and starboard sides, accurately mapping the three-dimensional plane of the waterline. Recording the amidships marks introduces a complex structural variable. A commercial ship acts as a flexible steel girder, meaning the hull physically bends under load. Heavy cargo concentrated in the center holes forces the middle of the ship to bend downwards into the water, a condition called sagging. Conversely, stacking heavy mass at the extreme bow and stern causes the center to bow upwards, a structural condition called hogging. Averaging only the bow and stern draft marks on a sagging ship completely misses the deep bulge of steel in the middle, failing to account for thousands of tons of displaced fluid. To solve this, the chief officer calculates the mean of means, applying a specialized averaging formula to the 6 distinct readings. This calculation heavily weights the amidships draft against the far ends, mathematically smoothing out the exact longitudinal bend of the hull. Processing this deformation ensures the crew derives a precise displaced volume, preventing the calculation of thousands of tons of phantom cargo. We now possess an exact volume. But the Archimedes Principle specifically correlates ship mass to the weight of the displaced fluid, meaning volume alone is incomplete. We must multiply that volume by local water density. Depending on the exact salinity and temperature, the physical density of the marine environment shifts drastically. These volumetric models illustrate the baseline constraints. Pure fresh water has a density of exactly 1,000 kilograms per cubic meter. Dense ocean saltwater carries dissolved minerals, typically sitting at 1025. To displace its own weight in less dense freshwater, an identical ship sinks physically deeper into the fluid to achieve equilibrium. Commercial terminals are frequently built in estuary environments where tides constantly mix salty ocean water with fresh river runoff. Because this mixture is entirely unpredictable, crews must drop a bucket to physically draw a sample of the exact water the ship is resting in. They float a highly calibrated glass hydrometer in the cylinder to measure the precise specific gravity of the local environment in real time. Omitting this localized environmental measurement breaks the arithmetic. The local fluid strictly dictates the mass conversion. Building to a conclusion, the structural volume derived from the physical draft marks and the local density derived from the hydrometer complete the empirical model. Multiplying the corrected volume in cubic meters by the specific local water density produces the total displacement mass of the vessel in kilograms. Conducting this strict survey once on the empty vessel and a second time after the cranes stop loading yields two verifiable metrics. Subtracting the empty mass from the loaded mass extracts the exact, legally binding weight of the payload for commercial sale. Operationally, tracking this localized mass distribution ensures the master knows exactly how the payload is straining the steel hull against its engineered limits. Complex global supply chains manage billions of dollars of raw material entirely by applying ancient hydrostatics against a painted steel wall.